Can we draw the resonance structures from this one? Here, electron deficiency, we've been talking about, in order to accept the electron, there's got to be electron deficiency. And then thankfully, we have a positive charge carbon there. So something can accept the electron. So that sounds like a good candidate for making resonance structures. Okay? So can we make a resonance structure there? Answer is no. There's nothing to move. There's no double bond nearby, no lone pair nearby, right? It's not just electron deficiency alone makes it happen. You gotta have something to give or something to accept, right? You have to have those pairs. Otherwise, not happening. So that one, no matter what you try, you're never gonna get the resonance structures. So whenever you draw the resonance structure for a situation like this, we'll take the points away. So you gotta be careful when you draw the resonance structures. It's a random approach. I'll just give you 1,000 different resonance structures. You find the right answer from there, and they give you all the credit. That type of shotgun approach doesn't work. Believe me, people try it. And it'd be hate to see that. What about the next one? Can we draw the resonance structure on that? It's kind of same structure. We got the positive charge carbon right here. And the double bond here. So double bond means that there's an electron to move. And then in the adjacent carbon, you got the electron deficiency. So this is the one that we showed before. This pair of electron making double bonds, that electron can move over here. That moves the double bond between those two. And that fills up the balance for this carbon. So it's no longer possibly charged. But that leaves the electron at the vacancy of that carbon. Now that carbon becomes a possibly charged. This is a valid resonance structure. So you can go. Between these two, which one is a major or minor? I would say both are equivalent. So both are major. 50-50. What about this one? Can I draw the resonance structures? I don't see no double bonds. There's no triple bonds. So no resonance structures. I told you a lone pair also can move. So nitrogen is a lone pair. If this is a carbon, it's impossible unless you got negatively charged. But this nitrogen is a lone pair. The lone pair can move and make a double bond between those two carbons. That's going to make the positive charge go to nitrogen. But this nitrogen positive charge is not that unstable because this nitrogen has an octet field. If you count all the electrons, there's 4 electrons are shared between this carbon, 2 here, 2 there. So nitrogen has an octet. So this is actually a pretty stable nitrogen, even though it's a constant charge. Anyway, this basically says that lone pair can also participate making resonance structure. Not only the double bonds, not only the triple bonds. All right, these are simple ones. Yeah. Well, that's the formal charges. If you do the formal charging formula, you're going to find out this nitrogen is going to get 1 positive charge. The reason is nitrogen is when it's a neutral, it has an lone pair. You see that lone pair is gone. It's the bonds, extra bonds are made between these two carbons with the expense of the lone pair. So that lone pairs are now shared with the carbon. Share means that one carbon get the 1 electrons. So nitrogen gives the 1 electron for the lone pair to carbons. From the perspective of nitrogen, it just lost the 1 electron by the making the resonance structures. So that's what's possibly charged. Formal. That's the formal charging. Yeah. Right, I can hear you.
The nitrogen that has the low pair would be major, while the nitrogen that doesn't have the low minor.
Oh, which one's a major and minor? Okay, so that's a good thing. Well, think about this. Nitrogen is a positive charge. Carbon is a positive charge, right? But this is nothing to so that which one gets charged here. If you look at that, this nitrogen has an octet field, right? And also this carbon has an octet field too. If you look at this one, nitrogen neutral, it's an octet field, but this carbon, 6 electrons, that's an octet. So this is less stable than this one because the octets are not meant for the carbon. So this is a minor, that's actually a major. Good point, I forgot to mention that. All right, so you gotta look at these things very carefully. I'm pretty sure that right now, during the one resonance structure, you're gonna think so many things, but this is gonna be naturally flowing as we keep going this class. So this is something you're gonna keep practicing. That's why, after today, I really want you to draw the 100 resonance structure of the whatever molecule, get used to these things, finding out what you can do, what you cannot do. You can challenge it with your friends, ask them to draw the resonance structures, things like that. There's a lot of things you can do. All right, having more, this one, can you draw the resonance structure? And then I said no here because the electron cannot move there, but actually I just found out the flow of the question. The resonance structure is still possible, even though this is not a good one. So let me show you instead of that, what we can do. We can kind of always draw, making the electron move to here to there. That's what I'm trying to tell you. This double bond cannot move here because these coordinates are completely filled up. Now it cannot accept anymore. But the resonance structure that I was thinking about possible is this one. That makes this positively charged, that negatively charged. We just break the double bond, electron pairs are making a double bond, we just give it to this carbon, so we got the charge separate right there. Octets are not met, so that means that these are definitely minor contributors to this. That's possible, but other than that, there's nothing else. But this one is something that we know, electron pairs can move here. We just talked about that's possible because electron can come from these double bonds given to this carbon that only has 6 electrons, so there's a room to accept. So that makes a resonance structure that we've been talked about. What I'm trying to tell you is we can kind of do that with a positively charged molecule. What about the negative charges? And now, I've been telling you, look at the molecule from the left side, and suddenly ask you to look at the molecule from the right side. That's kind of thing. And this double bond move there to this way, making things like that move. What is a negatively charged carbon means? When this positively charged carbon means, there's how many hydrogens this positive charged carbon has? Is it over 2? If it has a 2, it shouldn't be charging. It has only 1. So that's why this is a 6 electron carbon here, because of 1 hydrogen. What about negatively charged carbon? How many electrons, how many hydrogen this carbon has? 3? Well, you're talking about this? That's a 5 bonding carbon. There's no way we can have that. What this negatively charged carbon means, it has only 1 hydrogen. This negative charge is extra pairs of electrons. That's what that means. So that one still have a 1 hydrogen, but it is a lone pair. So that's what this negatively charged carbon means. The positively charged carbon, on the other hand, and that's negatively charged, means this. Just same just 1 hydrogen, but the number of electrons are different. No lone pair, right? And then lone pair there. So that's what makes it positively charged, negatively charged. So carbon normally have 4 bonds. This only has 3 bonds. So this double bond can move over there. Then if you double bond move from here to there, then we're going to make this carbon have more than 8 electrons. Because if you count electrons on this carbon, it's already 8 octets are filled. So you cannot accept anymore. So does it mean that we cannot draw the resonance structures? You're going to think other ways. You cannot give electron to this carbon, but that lone pair can move to the other directions. It goes this direction. The electrons comes in, so you make a double bond. This pair electron comes to that carbon. We are moving negatively charged, negatively charged. So that is a value. So what goes where is depends on what you're moving. Yes. No, it's not a mirroring. It's actually moving the electrons. But it looks asymmetrical. That's why you think it's an asymmetrical situation makes the resonance structures. But you gotta think that it's causality, right? What the cause is electrons moving. Reality is that it becomes asymmetrical. It looks asymmetrical. But the reason why this resonance should happen has nothing to do with the molecular groups asymmetry.
Like the trend of it being asymmetrical.
Well-
Does it, like mean that the electron is like moved to the other side?
So-
It's not like-
Yeah, I know. This is a concept that you have to think about carefully. Well, basically, what the resonance structure stand for is a other possibility of having locate electrons somewhere else than what's drawn, right? So let's say this one, we got the electron sitting there, extra electron sitting on this part. Right? If there's a no double bond, this cannot connect, right? Because of this double bond, double bond electron can move out. That's the reason why we can move the resonance. So it's something to give, something to accept. You have to match it. If you don't have a double bond here, still the molecular looks asymmetrical, but the resonance structure not possible, even though they look asymmetrical. So that's why symmetry is not the determinant. It just happens by the resonance. That approach. All right, so that is kind of telling you not only the positive charges, you need to think about the negative charges as well. That can make a resonance structure too. Lone pair situations, well, I put a lot because can you make a resonance structure from this one? Nitrogen is a lone pair, but you don't see any of the electron deficiency or the excess in the nearby, right? So you cannot make a resonance structure with that. But what about this one? Can you make a resonance? This one, yes. Lone pair nitrogen comes in, that makes a double bond between the carbon and nitrogen. But if you stop there, obviously that's invalid. But synchronous to that, you make this double bond electron to go to this carbon, then you can make a resonance structures. And this becomes a minor contributor to this one because of the charge separation. If you look at the octet, all the atoms here met an octet. Even though these carbons are negatively charged, octets there, nitrogens are positively charged, octets there. So the reason why this minor contributors are nothing to do with an octet, because you make the carbon having a negatively charged, that is not really good for the nature. And then this is a neutral related. What about the other way? Can we move the electron here to there? Yes, different direction. Then your answer should be no, because if you make this electron pair to go to nitrogen, nitrogen cannot have a 10 electron by having extra pairs of electrons. So the same reason, it cannot accept it, coming from the double bonds. What about this one? Well, there's a positive charge here. We're thinking electron move from here to there. This comes in, this doesn't fly over there. It only move to the next one. So this one comes in, they got double bond between these two, but that makes this carbon 10 electrons. So you gotta give up something. But thankfully there's a double bond. Maybe it can go there, but instead of going there, you maybe go here. So two pairs of electrons move together, but it can actually make a new resonance structure this way, and that becomes a very valid. And then between these two, which one do you think is a major? Which one's a minor contributor? To talk about the major minor, probably you need to look at the octet things first, right? And this is a nitrogen positively charged, but it has 8 electrons. This is an octet filled. That one, these carbons have only 6 electrons, so that's an octet not filled. You can easily say that that's a minor contributor, that's a major contributor. Right? What about this one? Now I just change the charge into a positive negative. It looks same. So if you practice with that, and then you just memorize, oh, I just moved the electron this way, then this will happen. If you do that same thing to that molecule, the answer is going to be invalid. That's why this thing you cannot memorize. If you memorize how just patterns of solving problems, we'll lay a trap like this. And you're just going to say, yeah, I can do the resonance structures. This comes in, that goes out, and that's a really bad resonance. So that's why you have to understand why things go, where things go, what's the reason for that. This is the negative charges covered here. So if you're trying to move this one there, then this cannot accept. This comes from this side, and then that goes there, that's not possible. So this one, you cannot have a resonance structure this way. You can have a probably some other minor contributor from that one, but not this particular way I show of I mean, there are other resonance structures possible. I'm not saying that it will never make a resonance structure, but not the one that you will see here. So that's why I keep telling you, can do anything, actually makes it more difficult. And in resonance structure, open, it's like that situation. It's very open format. Unless you violate any rule, you can do anything. And that's kind of what the electron's going to do. It can go anywhere, as they can go. But they cannot go to the place they cannot go.
This one. That the nitrogen has a lone pair aspire to be having the from it seems like the carbon
This carbon has a deficiency there, right? That is a 2 hydrogen and then 1 carbon bonded. That's for 6 electrons. So this is a one that has an octet not man. But by moving electron from here to there, now it becomes a part double bond. So now it gets that electrons, now the octet's meant for that carbon. Yeah, that's for the forward charging things. And then with the line we're drawing, because we don't typically show the hydrogen, that can create a trouble like this. So that's why you gotta practice. Whenever you see things like that, those how many hydrogen is gonna have, right? Even that simple question, a lot of people make a mistake in the beginning. So you gotta do not go home with it. All right. So not really simple, right? It looks simple in the beginning, but when you trying to put things together and then make the molecule bigger, it becomes a little challenge. This one and that one. This one, you know, the difference is, you know, you can make the pi double bonds, electric double bond move around, but you cannot come out to nitrogen because nitrogen cannot accept. It's already have 8 electrons there. They cannot accept anymore. But this one, why it can come out this way? Because it goes in here, but these double bond electrons can go to the carbon. Even though that's not really great, but at least a possibility exists. So that's why it can happen that way, not the other way. Anyway, I hope that these things make you think. That's the word. And that's what you need to do when you draw the resonance structure. All right, continuing. I just talked about the simple situation. You just make a one resonance structures, but sometimes it makes it more than one. So look at that one. You got the electron deficiency on this carbon and double bond next to it. So now we know these double bond electrons can move over there. That makes a double bond between these two, and then make this carbon electron deficient. So that's what positive charges move over there. So it makes a resonance structure. And then you may find it happy. Oh, I drew the right resonance structures. And if you stop there, then you're missing another one. So these positive charges next to an oxygen with a lone pair. And we talked about the lone pair can move. So oxygen lone pair, if it comes in between the carbon and oxygen, it makes a double bond. That's the one that makes oxygen positively charging. So it makes a 2 resonance structure. So what is things to learn? When we ask you to draw the resonance structures, we never tell you how many you need to draw. It could be 1, it could be 2, or it could be 10. I don't know. So when I'm expecting 1, when you draw 10, basically what you mean that you got 9 wrong. That's bad. When I'm expecting 3, you only give me 1, you're missing 1. So basically that's the reason why the resonance structure questions are somewhat challenging. How many do you need to draw? Right? You don't know. I don't tell you. You need to figure it out. The electron can move around as long as they can. So you're going to find out how much they can by drawing one by one. And figuring out what's invalid, what's valid. Draw with the valid one, cross out the invalid one, then I guess you'll get an idea. So this one, can you make any resonance structure further? Now the oxygen lone pairs there, can you move to the other directions? That's the kind of things we practice. This been moving this way because there's electron deficiency. Electrons can be given this way, but there's no vacancy on the other side, so you cannot cross over. That's the bad end. You cannot go anymore. So sometimes you got to look at what's good, what's bad. That's why we did the things earlier. So anyway, among these 3 resonance structures, which one is a major? And which is a minor? I mean, some things are positively charged, like carbon, oxygen. And then I told you that whenever you try to decide that, we get the octet, right? This is a 6-electron carbon. That's a 6-electron carbon. Does this oxygen has a 6 electron too? What's not shown is that this oxygen has a lone pair, still have a 1 lone pair. 1 lone pairs are used to make a double bond, but they still have a 1 lone pair. So these have a double bond, single bond, meaning that 4 electrons are coming to this way, 2 electrons there, 2 electrons as a lone pair. That oxygen has octets in that. So this is a major, those 2 are the minor. All right, look at that one. Now the resonance structures, now it's negative charges, right? So these electrons, so extra pair of electrons on this carbon can move in between these 2, make a double bond between these 2. That tends to make these carbon double bonds to that oxygen to carbon as negative charges. It makes a resonance structure. It doesn't stop there because you see there is if it can come in between those 2, then this can come out. You make an oxygen negatively charged right here. So it also makes the 2 resonance structures forward. Which one's going to be major among those 3? Well, if you look at the octet, this, even though carbon is a negatively charged, octets are filled, 8 electrons of this carbon. Same for that reason. Carbon, anion, typically have like 8 electrons still there. It just have a lone pair. That's the reason why the carbon becomes charged. Oxygen being a negatively charged, still have an octet there. So all of them has an octet, 8 electrons in their value. So this is not the reason for the octet. Why one becomes the major and the other is a minor. So how can we figure out which was a major and minor? Because all of them have an octet field. Well, that is something that we have talked about. Carbon being negatively charged, oxygen being negatively charged, which ones do you think is the most stable? If I give a really heavy weight for someone very tiny or someone very huge in muscle, then which one can handle it better? Right? Oxygen being electronegative atom, it can handle negative charges way better than carbon has. So which one's going to be more stable? That's going to be more stable than the other 2. Because carbon, now typically electronegative atom, has to handle extra electrons. It's a huge deal for the carbon. For the oxygen, yeah, it's okay, it gets there. So that's the reason why that becomes a major, not the other 2. Not the octet reason, though, right? So it's a different reason each time. Yes. This one, oxygens are positively charged because it's a lone pairs are being used to make a bond. That does not have an octet, not meant for an oxygen. If you count the number of electrons, these oxygens still have 8 electrons. 2 double bonds, right? A double bonds meaning that 2 pairs of electrons share 4 electrons, right? Share with this carbon. Single bond, so that 2 electrons share with that carbon, so that makes a 6. But what is not shown is a lone pair. say oxygen start with like a two lone pair, we just use one. So one lone pair should have remained. That lone pair makes extra two, that makes it 8. So even the oxygens are positively charged, that does not mean that it has only 6 electrons. That's the difference from the carbon. Carbon doesn't come with the electron pairs, and lone pairs, but oxygen comes with the 2, nitrogen comes with the 1. So that's what makes it a little bit challenging. Because when you draw the in line angle drawing, typically we don't draw the lone pair. I mean, we could, but a lot of times we don't draw the lone pair. So that could look confusing. All right, next one. With this molecule, how many resonance structures do you think you can draw? I mean, oxygens are negatively charged, so we are thinking maybe this one comes in, and then once you make a carbon oxygen double bond, then these carbons will have 10 electrons, so you cannot give up something. So this double bond goes out there. That's kind of a thing we've been doing so far. So you can imagine that, yeah, that makes a double bond between the carbon and oxygen, and this double bond becomes a single bond, and then electron pairs goes there to this carbon. Yeah, great. One resonance structures. Question is, will it end there? It has a double bond next to it, so the same thing can happen. These electron pairs come in, make a double bond. These electron pairs comes out, you make another one. Should it stop there? Can you go further? There is another double bond here, so this comes in, make a double bond. This comes out, it makes a 3. Can you do more? I know sometimes people just keep trying because they don't know when to end. That's why I keep telling you, you try to make the resonance structure from this one, right? You make this one comes in, then this gotta go out, then that actually makes that one. So you make the cycles. So now that's all the thing you can draw, not anymore. So these things are what makes a resonance structure challenging and what makes you, what need you to study for. It's not easy to make it as a question. All right. So among those 4, which ones are major, which ones are minor? Well, same thing. These are octet metal oxygen. These carbons are negatively charged, octets are met. But you know, oxygens can handle electrons better than the carbon. And besides, benzene, even though we didn't talk about this, but you know that benzene is a resonance structure, resonance stabilized material. When benzenes are intact, it's actually great stability in the molecule. So this is good. That's bad for 2 reasons. 1, carbons are negatively charged. 2, benzene is broken. So that's why this is a major. The other 3 are minor. Resonance structure is what? What can you draw? Well, it's pretty simple. One, yeah, you know the benzene, they make a resonance structure. That's basically what it stands for. So 1 in your carbon. Second one, you do carboxylate. The oxygen lone pairs comes in, make your carbon oxygen double bonds. This double bond goes to the oxygen, there's negative charges. So that's basically what we talked about. But sometimes after you see this, you don't start that. There's gotta be more than that. There have to be more than that. You just keep trying, even though you shouldn't try. That's sometimes always hard, not knowing how many you need to draw. If you try, this lone pairs comes in, and then this one given to that, just try to draw the resonance to somewhere. You gotta move the electron. You felt that I need to move the electron to somewhere. If you do that, you just break the bond. This is impossible. That's not possible. So, unfortunately, these 2 are the only resonance structure you can draw. Nothing more than that. But don't try too hard. So that's not possible. As I said earlier, their resonance structure doesn't break a single bond. But what resonance structure does is just an unambiguous location of the electrons, not breaking a single bond. This is not the transformation. Resonance structures, you have to think in the right way. This is not the transformation. They're just trying to describe what it is by using a multiple structures, hypothetical structure. Now it doesn't mean even though each of them shares some of the true nature. So that's why it's kind of a hard to get concept if you go deep. Anyway, sometimes they just draw any structure for no reason. They just say, okay, I gotta make another one somewhere. And if you draw things like this, there's no way you can get this from there. So, but if you try something like this in an exam, because if you just thought that I gotta give more, I don't know how this could be made, but I just draw it down there. Maybe luckily, maybe I can hit that answer. But the thing is, if you draw something invalid, we'll just take it out. We take the points off. So don't try to give it too many. That's something I said earlier. Shotgun approach, we don't like to see.